Hello everyone, welcome back to HP Gaming Garage. In this part, we'll continue learning more on the previous topic.
The third way to do balance is building a functional, fundamental model of how your game works. Actually relate things to other things with hard numbers and use those numbers and formulas to then predict whether something will be balanced or not. So, for example, if you're making a trading card game like Hearthstone or Magic the Gathering, where you have cards with mana costs on them, you might be able to create an actual math equation that puts numeric values on everything the card can do, and then, say, provide a cost to power curve that says maybe, a four cost card gives you 8 points of power and a 5 cost card gives you 11 points of power, and so on. And if you know what every effect in the game costs, then you can use this to identify which cards are mathematically too strong or too weak compared to others. Now, this method does require a lot of upfront work to generate those math formulas in the first place, and your formulas might be wrong. Initially, they almost certainly will be, where they'll tell you that, like, say, a certain card is overpowered, but in actual play, it just doesn't appear that way. So you can never really fully trust your mathematical models. You always need to corroborate them with actual play data and play experiences. You want to look at if you make a model, you want to look at the things that your model says are the most powerful and the weakest, and then see if there's a real correlation between the things that players tend to use or not use a lot and what they tend to win or lose with versus what your actual mathematical model says are the most and least powerful things. Building the models in the first place also means you have to understand your game at a pretty deep level. So early on, when your mechanics are rapidly changing and in flux, and you haven't even played your game that much, you might not even have the experience with your game to be able to derive any math from it. Also, you'll probably run into at least a few situations where you'll include really weird effects that are just so different from everything else that they just can't be mathed out. So for those, you'll have to balance those some other way. Still, mathematically modeling can be a very powerful technique. It can save a lot of time, especially for games that are very content heavy, because you can just churn out tons of content, run them through your formulas to balance them, and then it might not be perfect, but you'll know it's at least a reasonable guess that gets you relatively decent balance right out of the gate without even having to take the time to playtest. So it can be a huge time saver on larger projects. And lastly, we have what is called analytics, which is a kind of combination of playtesting and math done at a large scale. With analytics, you actually have the game capture some real-world data, which might be things like what characters players use, how long they take to clear a level, what strategies are the most popular, what's the average game length, stuff like that. And if you only do this with 10 players, that won't tell you very much. But if you have this kind of data from 1 million players, that gives you the tools to draw some very powerful conclusions about how the game is actually played in the wild, and with enough varied play patterns that it doesn't just rely on a few skilled playtesters. It's literally all your players. So analytics can be an extremely powerful tool to assist in finding balance problems and fixing them, sometimes before the players themselves even realize that an exploit's possible. Like the other methods, analytics has some downsides too. First, you need to be able to collect this data, which means programmers on your team have to spend time building an analytics engine, which is time that they're not spending building the actual game. Second, analyzing this data involves statistical methods, and statistics works best with large data sets. So if your game only has a few dozen playtesters, the data you get from analytics won't be statistically significant, so it won't be all that useful. And lastly, statistics is actually a very tricky branch of math. It's very easy to find a plausible explanation for your data that's very convincing, but also very wrong. And there aren't often a lot of sanity checks built in. So if you make a math error, it can very easily go undetected most of the time, and then you'll just have bad conclusions, and you won't even realize why. So now I'll take a little bit more time talk a little more about just some quick practical tools you can use right now to balance a game that you're working on. So first thing to realize about any form of balance is numbers do not exist in isolation. They're only meaningful in relation to other numbers. So say I'm working on an RPG and I tell you that the main character starts at first level with 50 hit points. Is 50 a lot or a little? Well, it depends. If we're playing Dungeons and Dragons, 50 hit points is a lot. If you're playing any Final Fantasy game since like the fourth one, your guy will get killed in a single hit by the weakest enemy. 50 hit points is nothing. So you need to think about how things are related. And the two most common ways to relate them are what I'd call transitive and intransitive relationships. Now, these are actual words I'm not making up. They come from the field of mathematics, and these terms are sometimes used in game design, though they're not super common. Transitive means that there's some axis of power that everything can be compared to. Some things are just more powerful than other things, and specifically, transitivity in math means that if A is better than B and B is better than C, then A is also better than C. In transitive systems, there's usually a cost or limitation of some kind to balance out greater power levels, and the game design principle here is that more powerful things should cost more. So in Magic and Hearthstone, for example, some cards might cost 1 mana, and other cards might cost 10 mana. You expect that a card that costs 10 to be a lot more powerful than a card that costs 1, and these can be balanced as long as the cards with the same cost are as powerful as each other, right? All the 1-drops are about as powerful as other 1-drops, and then 2 cards of different costs have the more expensive card providing the more powerful effect. That's transitive balance. Intransitive means you do not have this property. You might wonder, what kind of relationship is there where A is greater than B and B is greater than C, but C is greater than A? Like, that doesn't make sense mathematically. Well, the most obvious example is probably a game you're familiar with by now, rock, paper, scissors, right? Paper beats rock beats scissors, but scissors beats paper around in a circle. None of these is more powerful than the others. There's just play and counterplay. With intransitive systems, what you need to be thinking about is making sure that each option has a reason to exist, that there isn't some other option that does everything rock can do and more. Once you start doing mathematical modeling, you will at some point want to learn how to use a spreadsheet program like Excel or Google Sheets. These are just so useful and are widely used as tools by designers when it comes to balancing, because you can just type your math formulas in here and it'll do all the calculations for you. And if you make like one change to a formula, it just updates everything immediately. Fixing a formula or fixing a piece of data is just quick and easy if you know how. Spreadsheets actually have lots of other applications in game design apart from balance too. You can use them as grids like graph paper to make maps. You can use them to manage projects by keeping a list of tasks you need to do and when you need to do them by. Or you can use spreadsheets to just make big lists of game data, like keeping track of every weapon and all its stats in a bunch of tables that are easy to read and change and export to a form that a game engine can read. Another conceptual tool I use a lot is making diagrams that are just a bunch of boxes and arrows, where each box is some kind of thing in your game, some object or resource. It might be gold or cards or lives or health, or even something more conceptual and abstract like how much of the map you've explored or how much of the main quest line you played through. And then drawing a bunch of arrows to show which things affect which other things, and what can turn into what. As a very simple example, here's what an extremely scaled down version of a typical RPG might look like. You have combat at the top of the diagram that basically lets you convert health into experience points. Like you get damaged in a random encounter, but then you get XP at the end, and the amount of health you lose is mitigated by your combat stats. Like having higher attack or defense means you'll finish the combat faster and take less damage, and then you lose less health. And then when you get enough XP, you go up a level, which improves your maximum health and combat stats, which then let you take on more challenging combats, and the cycle continues until you're powerful enough to take on the final boss and beat the game. And this is just looking at the combat system. You might also see how you could add on to this to add gold, which is also dropped in combat, which is then used to buy equipment at towns, which then improves your combat stats further, or adding an exploration system where the player has to explore to find new areas with more challenging combats and better combat and quest rewards. I found that making diagrams like this, and I know you might look at this and wonder, is there like a special format to this? Is there something where dashed lines actually like mean something very special? There's no like universal format for this. It's just whatever makes sense to you. But I found that making diagrams like this can be very useful for just understanding your game fundamentally and being able to visually identify feedback loops, what your core loop is. You'll just have a series of arrows that are kind of going around and around in a literal loop. And if there are any mechanics in the game that seem disconnected from the core loop so that they could be eliminated. So it's very useful for understanding your game. Lastly, there's the rule of two. This is just a common guideline that says if you know that a certain number in your game is too low during tuning, but you're unsure whether to add +1 or +2 or +3 to it or whatever, in your next iteration, double it. Or if you know a number is too high, cut it in half. Now, this seems absolutely ridiculous. Like, if I'm currently have a number at 100, and I'm sure that the correct value is like 102 or 103, multiplying it by 2 means putting it to 200. That's going to massively overcorrect the problem. And yes, that is exactly what I am telling you to do. And here's why. First, if you don't know exactly what a number should be, that means there are parts of your game that you are still learning about that you just don't know that well, because you don't know what the right number is exactly. And so doubling a number is such a massive change that it will throw off a bunch of stuff. It'll fundamentally change how the game plays and give you a very good idea of what that number actually does and what it does and doesn't affect. So this doesn't mean that 200 is the right and correct number. It means that if you change the number to 200, you will get some very useful information on your next playtest that will let you understand your game much better if you try. Sometimes you'll even luck into realizing that if you make this kind of radical change, then it actually makes the game better in a way that you would never have even thought about before. Second, we do tend to underestimate how much we're off. So if you have a number at 100 and you think it should be 102 or 103, it could very well be that it should actually be 130 instead. And if you just incrementally change by giving it a +2 on every playtest, it's going to take forever to get there. If instead you double it, then you can zero in on the number very quickly. Right? Going from 100 to 130 in increments of +2 means it'll take 15 playtests to get there. But if we double it and have it back and pick halfway points, then we'd start at 100, double to 200, find that's too high, go back to the midpoint at 150, still too high, drop back to between 100 and 150, halfway there, so 125. And now already we're much closer to where we need to be, much faster with many fewer iterations. And we've learned a lot more about our game and the effect that this number has. Last thing, just remember what I mentioned last time, that major changes to the game's core functionality will throw off the balance. So getting the balance feeling right is usually something that happens much later in the design process after the mechanics are working and pretty solid. So, if you spend a huge amount of time getting the game perfectly balanced and playtesting for balance before it's even fun or otherwise meets its design goals, you're just going to have to redo that work later. The only reason to balance super early is if your balance is so far off that it makes further testing impossible, at which point the imbalance is going to be really obvious and the fix will probably be equally obvious. Also remember that making a game more balanced is just a means to an end. That end has to be whatever the design goal is for your game. Even if you're just trying to make a game that's fun, fun is not the same as balance. There are plenty of examples of unbalanced games that are fun despite their imbalances, and even examples of some games that are intentionally unbalanced on purpose, and the imbalance is the entire point of the game. So if unbalancing the game serves your design goals, then don't balance it. Make it unbalanced, but do so with clear intention.
Since game balance is actually one of my personal areas of specialization, I of course have a lot of additional resources for you this time. For one thing, as you can see in the lower right here, I've written an entire book on game balance, though I'll admit it's probably not something you want to buy just as you're starting out, just something to keep in mind. In a few years, if you get deeper into game design and feel like you really want to know everything you can about this one specific topic, remember that book exists. I've also included a GDC talk here that I've given specifically about balancing TCGs, which is basically chapter 6 out of the balance book. Below that is a video from Extra Credits talking about what happens when games are not balanced when it makes them better. Below that is another book called Playing to Win, except this one's actually available online on the author's website for free. And it talks specifically about the best competitive players and what they do to consistently win at their game of choice. This is not a how-to guide on game balance, but it does provide a mindset for how to playtest for balance, and also what your most competitive players will act like when they actually play your game. And lastly, because I mentioned resource flow diagrams, machinations.io is a useful online tool that lets you create resource flow diagrams in your browser and actually make them interactive so you can add numbers to them and watch them go up or down in order to simulate play. This tool does have a learning curve. It can be a bit fiddly at times, but it also does have some great tutorials and onboarding to get you up to speed. So if this kind of thing interests you, it's definitely worth your time to check it out just to see what it's like. And with that, I'll give you your regular reminder to take your assessment so you can get your certification from HP Gaming Garage. Thanks for watching, and I'll see you next time.